This video is a culmination of all the algebraic skills we've looked at over the last few weeks. It takes all the knowledge we have of expanding, factorizing, simplifying, and rearranging equations to solve them and puts them in the context of word problems. So we've already looked at similar things when we looked at working from word problems for algebraic expressions. So we're still using the same thing, but the big difference this time, as well as using our inverse operations and solving 2- and 3-step equations, so we're looking at life-related context or abstract context, so some sort of context behind it all. So when solving word problems, always state your variable. That's part of our communication, ensuring that I, as the teacher, know what you're talking about, but also any other observer or reader of your work can follow what you've done. Always look for those keywords we talked about previously with the algebraic expressions, such as less than, product, difference, sum. The key steps to solving word problems are identify the quantity, state your variable, search for these keywords, create an equation, solve the equation, which includes checking your answer, and interpreting that answer and writing a worded statement. Now, general rule of thumb for maths, if you're given a sentence, you answer in a sentence. Now these are not new, they also follow our see, plan, do, check process. So what we have here are some simple equations related to what we did with the algebraic expressions earlier. So there's 3 questions here, let's look at them one at a time. Here's the first one. I've already highlighted some of the key information, so we're seeing what it is. 6 is subtracted from our number. The result, which is another word for answer or equals, is 15. So we start with our number. Our number is going to be x. We state our variable, and we subtract 6 from it. X take 6 equals 15. It's one-step equation, so we reverse those processes using inverse operators or add 6 to both sides if we wanted to solve it. Okay, we're not required to solve them in this case. Second example is like this. There's a few different processes happening here. 3 more than 7 times a number is 0. So there's our equals there. There's the right-hand side of the equation. We're taking our x value, we're multiplying by 7, and then adding 3 to it. So state your variable, multiply by 7, add 3. The result is 0. The third example, a little bit more complex. When dividing a certain number by 2, the answer is 4 more than that certain number. So this indicates the answer is in the middle, the equal sign's in the middle, and we actually have variables on both sides, the numbers on the left and on the right of that equal sign. So on the left, we're dividing by 2, so it's x over 2. On the right, 4 more than means plus, so it's x plus 4. So let x be the number again. This time it's x over 2 equals x plus 4. So there's the green bit, there's the red bit. Now this time we're actually going to solve the equation. If 3 is added to a certain number and the result is multiplied by 12, the answer is 108. So I've already highlighted the key information. Let x be our number. You could use any letter. It could be n for number or y or z or k. First initial you have, doesn't matter. We're taking that number, we're adding 3 to it, and then we're multiplying by 12. So it's x plus 3. That's our first step, so we put it in brackets. So we ensure order of operations says we add first, and then we multiply that by 12. Okay, and it looks like this. That's what we've looked at before. When you write times 12, you're in bracket. Put the 12 out the front, we leave out the multiplier. So you've got a couple of choices at this point. You can expand the bracket, or you can solve normally. So we undo the 12 first, giving us 9 on the right. So 108 divided by 12 is 9. And then we take 3 from both sides, giving us an answer of 6. Alright, our next example is a real worded problem, in that it's trying to put it into a context or a real life situation. Take the time to look at what the important information is. The key question is, what is our variable going to be and how are we going to work that out? How do we know it's our variable? The key information here, let's have a look. Taxi charges are $3.60 plus $1.38 per kilometre. The fare was $38.10. What we want to know is this bit. How far did you travel? That's the key. Whatever the question's asking, that's our variable. So let's highlight those bits of information. So how far That's our first step. Let d or x be the distance travelled. From there we can work it out. Now taxi charges, what this indicates is that we have a flag for which is a cost no matter how far you travel, of $3.60. And then we charge on top of that the $1.38 per extra kilometre travel. So our equation is $3.60 plus 1.38 times d. And that answer was $38.10. There's our equation. Now we're going to solve it. So as we've done before, order of operations are multiplied by 1.38. And then we're adding 360. We want to work backwards through that, so we're going to do the inverse. So we're going to take that and divide that. So there's our equation. Let's undo it. We take the 3.6 away. We get 34.50, and then we divide both sides by 1.38, which gives us an answer of 25. Does that seem reasonable? Well, let's think about it like this. Substitute that back in there and work it out. We should get $38.10. Here's another example. This one actually uses variables on both sides. Take the time to look through the question and identify the key information, so you may pause at this point. So the key information for SEVA, $50 per day plus $1.20 per kilometre. Hertz, $40 per day plus $1.35 per kilometre. And we're renting for 3 days. The question is, how far can you travel? So the cost is the same. The cost is the same indicates an equal sign. How far is our variable? So our first step is to identify our variable. Highlight the information there. Now it would seem that there's actually two things that we can change, two variables, but for this particular case there's actually only one, because even though it says price per day here for both companies, the days is actually fixed at three days. So there's actually a fixed cost for each car for the day's travel. Our variable once again is distance, because that's what we're after. How far can you travel? So for SEVA, the fixed cost is $50 times 3 is 150. So that's our constant. For Hertz, same deal. 40 times 3, $120. So they're both constant values for this particular situation. Let's go to the next page. Our cost is our fixed cost plus our variable, which is $1.20 per kilometre per distance. So we're timesing by d. For Hertz, $120 is our fixed cost plus $1.35 per kilometre. Now, because the costs we want are equal, we make the equations equal. So we actually have these. Now, as we did before, we have more groups of d on the right. It's a larger number in front of the d. So we're going to group our d's on the right hand side and our constants on the left. So we take the 120 to the left, so it's minus, and we minus the $1.20 d on the right. Simplify by grouping like terms, we get 30 equals 0.15 d. So we solve that by undoing the equation, or by dividing both sides, the inverse operation, by 0.15. End up with 200. So our answer is, the cost is the same when he travels exactly 200 kilometres, because that's what d represents. How do we check our answer? We substitute back into these equations, there and there. So put 200 in for d here, 200 for d here, and they should both end up with the same cost. So we can extend on that idea further by looking at what that actually means. Because SEVA has a cheaper rate per kilometre, the further that he travels with SEVA, the better the deal, the cheaper the cost will be. Because Hertz has a more expensive cost per kilometre, the further you travel than 200 kilometres, the more expensive Hertz is. But the less you travel, Hertz is cheaper. So it looks a bit like this. So if we say, we were to graph this information, which we'll look at later, SEVA looks like this. Hertz might look like this. And this is your cost going this way. And this is your distance. So kilometres. Bit of a rough graph, but as we go further to the left, the Hertz one has a lower cost. As you go past that point, that's our 200 kilometres there. To the right, Hertz is more expensive than ABUS, and that's what that information tells us. That's what we just found, that point of intersection. So there's a couple examples of how we can apply our mathematical knowledge of equation solving to solving life-related problems.